Good morning. My name is Oh Bin Song, and I'm a graduate student of Hanyang University in Korea. My advisor is Professor Simon Song, and I'm going to talk about drag reduction by a layer on superhydrophobic surface in a Taylor-Couette flow. Numerous studies of drag reduction using superhydrophobic surface have been conducted for decades, and there are several reviews papers available in literature. In the past, drag reduction by the superhydrophobic surface was mainly confined to laminar flow. Park et al. Showed in their review paper that drag reduction reached up to 40% even under turbulent flow conditions recently. However, according to Rirabi et al., the air lubrication methods were often used in many turbulent conditions, and in this case, the stability of air pocket is very low for available surfaces. So an essential work which should be done in future research is trying to stabilize air pockets or air layer on superhydrophobic surface submerged in water. Recently, our team led by Professor Dong-Lip Kim have developed a novel superhydrophobic surface. It is made of PDMS and has a unique porous structure that provides a superior air retaining capability in water. The hierarchical structure of porous PDMS film was precisely controlled by ultrasonic spraying, so that small pores are in contact with water and large pores are located deep in the film. Then PTFE coating is applied to increase its durability. As a result, the contact angle of 115.6 degrees was obtained, and we found that an air layer was well maintained under a high shear condition in water. Our research object is to investigate the drag reduction caused by the air retaining superhydrophobic surface. For the first, to develop a Taylor-Couette flow device to measure torque precisely over a large range of Reynolds number with a single working fluid. The second is to visualize the Taylor-Couette flow field by using PIV. The third is to estimate the slip velocity and slip length. This is the schematic of Taylor-Couette flow device that we developed. It consists of two concentric cylinders, a torque sensor, motors. The height of inner cylinder is 220 millimeters, and the gap is 5 millimeters. A Taylor-Couette flow device is known to be suitable to measure torque precisely over a large range of Reynolds number simply by controlling the angular speed of circular cylinder. An issue here is that we need to maintain a single working fluid, which is water, over a large range of Reynolds number. Because we examined the drag reduction by the air layer on superhydrophobic surface. I'm not going to through the details of the device setup today, but we were able to operate the device over a shear Reynolds from 1,000 to 20,000 by taking into account of a small torque of bearing. This on the right is the PIV system for visualizing the velocity field. It is a normal to the PIV system that can measure streamwise and warm normal components of velocity vector. To validate our Taylor-Couette flow device, we compared dimensionless torque measured with a no-slip condition against other data published in literature. This graph shows that a dimensionless torque versus a shear Reynolds number. As you see here, the Reynolds number was covered from 1,000 through 20,000 with a single working fluid. Regardless of Reynolds number, our data are in good agreement with other data as you see here. Now this is a validation of PIV measurement against DNS result. We performed DNS also. for the same geometry of our Taylor-Couette flow device at Reynolds number of about 1300. This graph shows angular momentum plot. Due to persisting Taylor-Couette vortices at this Reynolds number, the angular momentum were ensemble averaged along the axis of Taylor-Couette device. The average angular momentum shows good agreement between PIV and DNS result. Now, this shows results of drag reduction. The effects of porous superhydrophobic PDMS surface on drag reduction was examined by comparing them against the same size but bare PDMS. Both PDMS film were attached on 1/5 of inner cylinder. This dimensionless torque was calculated under an assumption that the entire cylinder was covered by its one PDMS in both cases. As you can imagine, the drag reduction rate was different at a different Reynolds number. It was reduced by 80% at a low Reynolds number of 3000 and by 8% at a high Reynolds number of 16,000. As you see here, these are pictures taken after torque measurements. There are still air layer or air pockets were maintained on the porous superhydrophobic surface during torque measurement. I know that it is hard to identify the air layer with these pictures, but if you compare them to a picture of a surface without the air layer on it, you can see the difference. Now we visualized both the flows of no-slip and slip conditions by PIV. This is the mean velocity field contour. As you see, no-slip condition shows more frequent red than slip condition near the inner cylinder, meaning that the flow is faster with no-slip condition and there are slips on the slip surface. In order to make sure the slip on the inner cylinder, let's look at the angular momentum plot. This is the mean angular momentum profiles of no-slip condition and slip condition. The momentum was normalized with angular momentum of rotating inner cylinder. The radial position between the inner and outer cylinder was normalized by the gap between them. Near the outer cylinder, the two momentums are nearly identical. But if we look closely near the inner cylinder, there are distinct differences in the angular momentum. The porous superhydrophobic surface shows 14% less momentum than that of inner cylinder near the wall. With this data, we simply estimated the slip velocity and slip length 17.8 mm per second and 98 micrometers. We are still working on this project and hope to get data at high Reynolds numbers soon. Finally, our conclusions are we investigated drag reduction by the air retaining on superhydrophobic surface by using Taylor-Couette flow device, and we measured the torque and velocity field of the Taylor-Couette flow device for a wide range of Reynolds number using a single working fluid. We found that the drag was reduced from about 8% to 80% on superhydrophobic surface. The results of PIV measurements indicates that the slip velocity is 17.8 mm per second and slip length is 98 micrometers at Reynolds number is 1300. More data will be collected and analyzed at higher Reynolds number in the future.